If you scatter metallic and glass spheres across a table, they naturally roll apart into two distinct identifiable clusters. When we try to teach a machine to categorize these, the common instinct is to draw a straight, arbitrary line right between them. But training data is a controlled snapshot. In the real world, a wave of new, slightly unpredictable objects will fall onto this environment. If that initial line was drawn too closely to one group, the natural variance of the new data will bleed across the boundary and trigger a misclassification. The goal of machine learning isn't just to memorize what has already happened. It is to mathematically prepare for the unknown future. Relying on just any line is a liability. True predictive survival requires an algorithm that actively hunts for the absolute safest possible boundary. The support vector machine is designed to locate the widest possible gap between these categories. This optimized boundary is more than a single thin line. It acts as a thick, expandable band. This buffer zone inflates outward in both directions until it makes physical contact with the closest data points from each group. The expansion stops here, at these filled-in red and green circles sitting exactly on the dashed margin boundaries. These specific boundary points are the support vectors. They are the only pieces of data holding up the logic of the entire model. The algorithm assigns a weight of 0 to all non-boundary points, effectively deleting the rest of the dataset from its decision-making process. By ignoring the vast majority of its own evidence, the algorithm ensures its boundary is anchored entirely by the most difficult and extreme edge cases. In the real world, data often overlaps, making a perfectly clean gap impossible to find. If we force the boundary to remain perfectly rigid, a single outlier will drastically shrink the margin and ruin the model's ability to generalize. To solve this, we use a soft margin, a penalty parameter that allows the algorithm to negotiate with imperfect data. The model tracks these violations using epsilon values, mathematically measuring points that fall inside the margin or across the hyperplane. These values provide slack, intentionally allowing a few points to be misclassified to keep the boundary wide. Accepting minor, localized failures becomes a mathematical necessity to achieve broader, global stability in the face of noise. Some datasets are completely nonlinear, like a tight cluster of one category completely surrounded by a ring of another. Drawing a straight, flat line through this arrangement is impossible without failing on a massive scale. The kernel trick solves this by calculating hidden similarities between points to completely change the geometry of the problem. By projecting the data into a higher dimension, the algorithm can lift the outer ring away from the center. Now, a solid flat plane can slide between the two groups, severing them with a massive clear margin. When the truth cannot be divided by a straight line, the solution is to elevate the perspective into a higher dimension. Compare the fragile, arbitrary line from the start of this story to the massive, optimized buffer zone created by the support vector machine. If we introduce a new, highly varied wave of test data into this environment, the thick buffer zone absorbs the variance, ensuring all new data lands accurately in its correct territory. To survive the unpredictability of real-world data, you must build the widest possible margin of certainty. The support vector machine achieves maximum confidence by deliberately throwing away the vast majority of its own data. But what happens if, instead of ignoring the data, we gave every single discarded point a voice? We'll explore a scenario where 100 details repeat the exact same story next time.